Welcome to this explainer. Today, we're diving into the fascinating, totally invisible boundaries that govern exactly how and where industrial robots can move. When you step onto a modern factory floor, you see these massive steel arms swinging around with just incredible precision, right? They're welding parts, moving heavy materials. But what you don't see are the complex, multi-layered invisible boxes dictating every single millimeter of that motion. So let's make those invisible limits visible. To kick things off, we really have to ask ourselves a pretty perplexing question. Why might a perfectly programmed, highly advanced machine suddenly break down in the middle of completely empty space? I mean, imagine watching a robotic arm performing this flawless routine, and then for seemingly no physical reason at all, literally no obstacles in its way, it just stops. Or even weirder, it starts moving completely erratically. Well, when a robot hits one of these unseen boundaries, you're going to see it exhibit some incredibly strange behaviors. You might see sudden, super jerky movements, or the tool center point, basically the business end of the robot, might dramatically slow down or just come to a grinding halt. In some extreme cases, its internal joint motors might simultaneously attempt to accelerate to their absolute maximum speed. The poor robot literally gets stuck trying to move through empty, unblocked air. It's wild.
So, our roadmap for today covers 4 of these invisible boxes. We'll be looking at the physical box, the geometric box, the mathematical box, and finally, the safety box.
Starting us off with Section 1, the physical box, let's look at the actual boundaries of robot motion. The very first boundary we need to define here is the maximum space. If a robot had absolutely zero physical limitations, no safety stops installed, and was just allowed to stretch out as far as its mechanical joints could possibly go, this is the absolute farthest it could reach in any direction. Basically, it's the total maximum design movement of all the robot's parts. But, in a real factory, we obviously don't let robots just swing wildly to their absolute limits. Instead, engineers shrink that massive maximum reach down to a much safer, restricted space. By adding hardware like physical mechanical stops secured with heavy fasteners, or non-mechanical devices like limit switches and laser scanners, the robot's physical box is artificially confined. This keeps everything nicely under control. And finally, nestled right inside that restricted zone, we have the operating space. This is the exact dedicated area where the robot actively moves to perform its actual programmed task, whether that's welding a car door or assembling a tiny microchip. It is the tightest, most strictly controlled physical box on the entire floor. Moving right along to Section 2, the geometric box and the geometry of workspaces. Now, what's really fascinating is that engineers actually use pure geometry to calculate those exact operating spaces before a robot is even built. The type of kinematic chain a robot has deeply influences its capabilities. Basically, whether the joints rotate or slide dictates the actual shape of its invisible geometric box. For example, a type A chain, which has 2 or more rotational joints, sweeps out a spherical workspace. A type B chain uses a linear, sliding prismatic joint early on, and that creates a cylindrical workspace. And then there's type C, utilizing multiple non-parallel sliding joints, which generates a parallelepipedal, or just a box-like shape. So why do we even care about all these geometric outer boundaries? In a word, speed. Traditionally, calculating a complex robot's reachable positions meant generating this massive point cloud and testing millions of discrete points, which takes over a full second of computing time. That's an eternity in computing. But by using these algebraic geometric formulations, engineers can precisely calculate a robot's workspace in just 0.02 seconds. It is an absolute game changer for designing robotic workflows efficiently. Which brings us to Section 3, the mathematical box. Let's talk about singularities, or basically, what happens when the math breaks.
Okay, so a singularity is essentially a point in a robot's workspace where it loses 1 or more degrees of freedom. Mathematically, this happens when a calculation, called the determinant of its Jacobian matrix, drops exactly to 0. If that sounds complicated, just think of a singularity like a car GPS giving you a mathematically perfect route that tells you to physically drive straight through a solid brick wall. The math says yes, the algorithm outputs a path, but physical reality says absolutely not. The linear equations just suddenly have 0 solution. The absolutely crucial point here is understanding the specific conflict between limitless algorithms and physical hardware. You see, algorithms exist in a pristine mathematical world, where requesting a joint velocity of infinity is completely valid. Sure, why not? But our physical modals are bound by the real world. They have absolute maximum speed limits before they break down. Singularities happen when that limitless mathematical algorithm tells a physical motor to do something that's just completely impossible. And that is exactly what causes the robot to freeze or flail wildly as it frantically tries to spin its motors at infinite speeds. Depending on the shape of the workspace we talked about a minute ago, robots can hit a few different types of these math traps. First, you have a wrist singularity. This happens deep inside the workspace when the axes of joints 4 and 6 become coincident or parallel, which makes the wrist spin uncontrollably. Then there's an elbow singularity, which happens when the arm stretches too far out to its boundary, looking like its elbow joint is just totally locked up. And finally, a shoulder singularity occurs when the center of the wrist aligns perfectly with the base axis of joint 1.
Fortunately, we can actually outsmart these math errors on the factory floor just by changing how we tell a robot to move. Linear motion is used for path-critical tasks, like welding a perfectly straight seam. Because it requires complex kinematic conversions, it's highly vulnerable to those unpredictable singularity errors. But we can use simple joint angle motion for what we call air moves, which is just repositioning the robot through free space. Joint motion takes the quickest nonlinear path, bypassing those complex kinematic conversions entirely and safely avoiding singularity errors altogether. It's a really clever workaround. All right, let's wrap things up with Section 4, the safety box, and how we go about keeping human workers safe. Now that we've seen how these powerful machines are bound by physical constraints and susceptible to weird math errors, we have to look at how we use safety barriers to protect humans. The fundamental rule of robotic safety is incredibly straightforward. A person might be injured if they enter the maximum space fully or partially. Because we know these robots can move unpredictably if they hit a singularity, keeping humans out of that unconstrained maximum space is an absolute non-negotiable necessity. So let's look at how this builds into a highly practical hierarchy of safety protocols. Step 1. We restrict the robot to only a portion of its maximum space. Step 2. We minimize the size of that restricted space as much as operationally possible. Step 3. We conspicuously identify those boundaries so workers know exactly where they are at all times. And finally, Step 4. We carefully design the area to avoid creating any trap or pinch points within that space where a human could potentially get crushed. To actually enforce all of this, limiting devices are used to literally shrink the box around the robot. We use mechanical stops, like heavy bolted steel blocks, to secure the hard physical boundaries so the arm physically cannot swing past a certain point. Meanwhile, non-mechanical tools like light curtains and laser scanners actively monitor the zone. If a human crosses that invisible laser boundary, the system instantly cuts the power, effectively and safely caging the robot inside its restricted space. But hey, what if we want to remove the cage entirely? If we actually want humans to work side by side with collaborative robots, often called cobots, we absolutely have to rely on additional, highly advanced safety functions. We're talking about safety-rated monitored stops, hand-guided controls, and speed and separation monitoring that actively slows the robot down the closer you walk to it. They also use power and force limiters, ensuring that if a robot does accidentally bump into you, it stops instantly without causing any injury. To wrap up this explainer, I'll leave you with this thought. As we master these invisible mathematical algorithms and physically adapt our geometric boundaries in real time, what will the shared human-robot workspace of tomorrow actually look like? We are constantly redrawing these invisible boxes, pushing the absolute limits of math, geometry, and safety to build some truly incredible things. Keep exploring, and thanks so much for joining me today.